Welcome to Ask and Learn.
In this problem, we have a thermodynamic cycle where we have an ideal gas in a piston cylinder device, and it's going a cycle. Well, from 1 to 2 here, we have isentropic compression, and also it's adiabatic there. So we go from T1, which is 20 degrees C, up to a different temperature as we compress the gas. The entropy doesn't change, or the specific entropy doesn't change during that process. And we go from a volume, we compress the gas by a factor of 5. So the volume at 2 is 1/5 the volume at 1. So and then this is a line of constant entropy. So I guess put some arrows in here how the cycle goes. The numbering should make it clear, but so from 1 to 2, then, so that means we have this compression ratio of, there's a factor of 5 there. From 2 to 3, we have constant pressure heat transfer. So we have heat being added to the gas, is heating it up, and we keep the pressure constant. So again, we let the volume change, but we keep the pressure constant. And then we let the volume get back up to what it was initially. So this is another factor of 5 here. You have a volume at 3 is 5 times that of the volume at 2. And so then heat is, as we drop the pressure back down, we have at a constant volume. Okay, so we drop the pressure and then we have heat transfer out. And so over here we have a constant pressure line here, and then a constant specific volume line here. So we have work being done from here to here, and then from this work positive, and then the negative work is this value here. So the net work that we're going to wind up calculating is the volume of this. So let's see here. What can we do here? Well, we're given some ideal gas constants. We're given R and CV. We can find Cp because that's just R plus Cv, and then we can find K because that's just Cp over Cv. And now for an ideal gas undergoing isentropic compression, we have this relationship between the temperature and the specific volumes. We know what this ratio is. This is just R12, so this is a factor of 5. So V1 was 5 times V2. And so we know everything here, and we can plug in, and we get that we raise the temperature from 20 degrees C to 540, so about 397 Kelvin to about 584 Kelvin. So we raise the temperature up here as we compress the gas to a fifth of its volume. And in doing that, we put some work into the system, and that work is given by for an ideal gas undergoing, let's see here, isentropic compression. We have that it's CV times the change in temperature. And in the end, that winds up being 204 kilojoules per kilogram. And we had no heat transfer during this first stage of the process. Now, for ideal gas with a constant pressure, from 2 to 3, we have T3 over T2 equals V3 over V2. V3 is V1, so we start back here and V1 over V2 is just R12 or 5. So T3 is 5 times T2 or 2,922 Kelvin. So this scale is way off because this temperature should be 5 times this temperature. So, you know, this is kind of going up a little bit here, and then this way goes way up here, and then comes back way down here. So this is not to scale, but it's a representation of the cycle. Um, Now, from 2 to 3, we have work being done, um, work coming out, and that's just because it's a constant pressure, it's just that pressure times a change in specific volume. And because it's an ideal gas, we have that ends up being the um, ideal gas constant times the change in temperature, and that winds up being 701.3 kilojoules per kilogram. So that's the work we get out there. Now we need the heat transfer that came in here. So as we were putting heat in, we get let's see here, we have the heat in. If we do basically an energy balance from between those two states, the heat in over that state is the work out times the change, or plus the change in internal energy. And again, just using the definition of enthalpy, we can figure out that this is just actually the change in enthalpy. And the change in enthalpy is the heat capacity constant pressure times the change in temperature. And we have everything, we know all of these values, and that winds up being 2,338 kilojoules per kilogram. So that's how much heat we put in here or here. And now the heat that we dumped out of the system as we were letting the pressure back down to our initial state, that is just the change in internal energy from, because there was no work done here. So that's just the change in internal energy in the gas from 3 to 1. And that is the heat capacity constant volume times the change in temperature. So the heat transfer, the heat that we got out was 1,840.3 kilojoules per kilogram. Now, let's see here. We should have let's see here. Then we have, so we have that, and we have no work in or out here because the volume didn't change. So we know the net work out is this value here, 497.3 kilojoules per kilogram. It's the work out minus the work in between these processes. You can also see that, let's see here. Yeah, I mean, there's a conservation of energy here too. So we can see here that, let's see here, this and this equals this, pretty much, close to it. Anyway, within rounding errors. And so then we can figure out the efficiency because we know the net work out and we know the heat transfer in. So the efficiency is just this net work out divided by the heat we put in, and that winds up being 21.3%. Now they ask us to figure out this what this efficiency is in terms of just symbolically. So it winds up just being a whole lot of algebra here, and I'll go through it in a little bit. And we're just going to basically use all these formulas here, but not plug in values. So here is the mess of algebra, and I'm not going to go through in complete detail because hopefully you can follow things. But we know the thermal efficiency is the net work divided by the heat transfer in. The net work is the work out during from 2 to 3 minus the work in from 1 to 2. And so this work out is R times T3 minus T2, and then this work in is CV minus T2 minus T1, and the heat transfer in is CP times T3 minus T2. So expanding this out, this first term just becomes R over CP, and then T2 is T1 times R to the K minus 1. So that's here and here. T1 we're going to leave the same. T3 is T2 times R. So here's T2 and here's R. And so now we can factor some things out and lots of things cancel. We can see that T1 goes away. So actually our reference temperature or whatever the temperature we're doing this at is irrelevant to the efficiency. So our reference temperature goes out. We get R to the K minus 1 drops out. And so we wind up with this expression here, which is nice, but we can do a little bit more to it. We can say that R over Cp, we can figure out in terms of K, and that is 1 minus 1 over K. So that's R over Cp. And then we can do a little bit of factoring on this guy here. Okay, we can get a common denominator here. And then we can get a common denominator between these terms. And everything, we expand everything out, and we see that we get an r to the k minus 1 minus r to the k minus 1. That goes away. And let's see here, we wind up, in the end, we just grab 1 minus r to the k minus 1, all over k times r minus 1 to the r times r to the k minus 1. Okay, so this is r to the k minus 1. So this minus 1 is not in the exponent here. And we can see here that, obviously if the compression ratio is 1, things get weird. In fact, we get 0 over 0, right? So no matter what k is. And then, we could plot this and figure out how we could improve the efficiency. Changing the gas, we could change k. Changing the compression ratio, we could change the efficiency. I'm pretty sure as the compression ratio goes up, the efficiency will go up. So let's see here, if R is big, then we get R is big compared to 1. We get R to the K. Let's see, if R is big compared to 1, then that goes away, and that goes away. And so we get R to the K over R to the K. So the compression, it actually, as the compression ratio gets large, this asymptotes to a value of 1 over K. So our peak efficiency, I guess, would be 1 minus 1 over K. So again, we would want K to be as large as possible if we wanted the efficiency to be as great as possible.